Good morning, guys.
Good morning.
Good morning. So you can hear me well, I guess?
Yes.
Yes.
Thank you. It's Friday, October 23rd. And we are discussing chapter 8. We're talking about nucleic acids, nucleotides and nucleic acids. We have three more lectures on that, right? 3 more lectures today, Monday, Wednesday. And then on Friday, we have a test. So right after this lecture, I will send you some pages from the textbook, which you should focus your reading on. Okay, so I didn't forget about that. I'm working on that. So, and of course, you're welcome to ask many questions. So let me initiate the screen share. Screen share.
Dr. Kornejko, did you decide how many questions were on the exam?
Yeah, so there'll be 25. So we had 30, now we're going to have 25.
Okay.
So still, I think it's a good balance. It's a good balance. The questions will be sort of similar difficulty as on the first test, but you'll have a bit more time to to work on them. Okay, so for the screen share, so last time we finished by talking about nitrogenous bases, right? So we talked about pyrimidines and purines, and we talked about there are 5 bases total, right? There are 2 purines, adenine and guanine, right? So we talked about those. And remember again, the easiest way to differentiate between those is that guanine has 3 hydrogen bond donor acceptor, and adenine only has 2, right? So you can see here, this position is CH. And remember, when you have a proton or hydrogen on carbon, that is not capable of hydrogen bonding, right? It's only hydrogens which are on heteroatoms, which are capable of hydrogen bonding. And obviously, this carbon doesn't have any lone pairs, so it cannot be hydrogen bond donor, and it cannot be hydrogen bond acceptor. So that's how you should approach remembering adenine, right? 2 hydrogen bonds, guanine, 3 hydrogen bonds. And remember, guanine will base pair with cytosine, and adenine will base pair with thymine in DNA or uracil in RNA. DNA and RNA. And the way to remember that is, again, guanine can do 3 hydrogen bonding. You can see there's hydrogen bond acceptor, lone pair, hydrogen bond donor. So 2 hydrogen bond donors, 1 hydrogen bond acceptor. So it will base pair with cytosine. So we'll go to cytosine. And now you can see there are 2 hydrogen bond acceptors, right? There are 2 lone pairs and 1 hydrogen bond donor. So, so using, I guess, analogies like that, you can, you should be able to remember these structures and remember how to draw the base pairs. And here is thymine and uracil, and remember the main difference here is the presence or absence of this methyl group. right? And remember how numbering goes. We talked about numbering. Start with one nitrogen and go the shortest route towards the second nitrogen, right? So 1, 2, 3. And so this position where the methyl group is position 5. So thymine is a 5-methyl analog of uracil, right? So you will put the methyl group at position 5, away from this nitrogen. So those are pyrimidines. All right. So as far as the nomenclature goes, so this is a little, could be a bit tricky. So as I mentioned to you, the names don't necessarily, cannot be necessarily categorized very easily, right? So that you can have to sort of, in a way, half memorize, half memorize and half remember some trends. Okay, so let's start with bases. So there are 5 bases. So adenines and guanine. So these are purines, and cytosine, thymine, uracil. Okay, so these are bases. No ribose, right? No ribose. When you don't have any ribose, you just go by nitrogenous base. Now, once you add a ribose, no phosphate. So ribose, but no phosphate. So that will be a nucleoside. No phosphate. Right, so in other words, you will have a structure like that. So ribose and nitrogenous base. So here then we add, so for adenine, adenine becomes adenosine. And again, depending on whether you have or not the hydroxy group at this position, right? So remember, there's always hydroxy group at C5 prime position, C3 prime position, and 2 prime may or may not have the hydroxyl. So what I will do, I will draw a hydrogen here, but in parentheses, I will draw an OH. So it could be either one. Okay. And so for adenine, there are 2 kinds of nucleosides. There's adenosine and deoxyadenosine, right? So adenosine will be the one with the hydroxy group, and deoxyadenosine is the one without the hydroxy group. So this position 2 prime, 2 prime, 3 prime, 4 prime, 5 prime, 1 prime. All right, so for guanine, it's guanosine. So just like adenosine, it's guanosine and deoxyguanosine. Now cytosine, so now I guess this needs to be changed because we can't really use the same suffix as we already have, because then we will not be able to tell the base apart from the nucleoside. So it will be cytidine. Cytidine, deoxycytidine. Thymine, thymidine, deoxythymidine, and uracil becomes uridine. So this is something you would have to memorize, right? But you can see there are some trends, right? And also practice. Just keep practicing, keep going over the slides. Maybe even sort of try to draw this table for yourself, sort of on a blank sheet of paper. You know, basically create 4 columns. Okay, so base, nucleoside, nucleotide, and then nucleic acid. and try to write these words in, okay? And ideally, I would even create the 5th column, okay? And here I would put the structure, at least the structure of the base. Assuming that you will be able to actually to draw the base attached to the ribose. Okay, then nucleotide. Nucleotide, now we have ribose and phosphate. So ribose, so base, ribose, plus phosphate. So that will be a nucleotide, right? So we have ribose, base, oxygen, and phosphate. All right, so here adenosine becomes adenylate, deoxyadenosine, deoxyadenylate. Now this one's actually pretty straightforward because each of these has the suffix ate. Okay, and so I guess 8 is because remember when you have a acidic residue, when you have deprotonated, so this is the suffix which is used. For example, acetate, propionate, formate, right? And so these are, remember, the phosphate will have basically will be deprotonated. So this is a conjugate base of the phosphoric acid monoester. So if you have phosphoric acid, remember phosphoric acid will have 3 oxygens. And so one of these will be attached to the 5' of the ribose, and these 2 will be deprotonated, right? So this is so this suffix will tell you that this is the conjugate base of the phosphoric acid monoester. Okay, cytidylate, deoxycytidylate, thymidylate, deoxythymidylate, and uridylate. All right. And of course, every time you see deoxy, that's a component of DNA, right? If you don't see deoxy, that will be the component of RNA. And obviously, uridylate does not have deoxy, or uridine does not have deoxy, right? Because this is just a component of RNA and cannot have deoxy. Do you have any questions, guys? All right.
I did have a question. For thymine, how is it possible to still have a thymidylate if it's not if there's no RNA? Does it make sense if thymine is not RNA?
Yeah. So this actually a very good question. I don't know if I can give you 100% convincing answer, but in general, when we talk about DNA, we do not often say that this is based on deoxy. We do not often use the deoxy prefix. So for example, on the next slide, I'll just show you in a moment. Because majority of genetics, right, is based on DNA and DNA manipulations. And so often scientists who work with DNA, they drop the prefix deoxy. They drop the prefix deoxy, and they just would refer to this as thymidine or thymidylate, knowing that they're working with DNA. So if everybody knows that there is no hydroxy group there, you do not need to continue emphasizing that. Okay, does it sort of make sense? So
Yes.
so it's based on just the widespread research in the science of genetics, and people just like in organic chemistry, we often take shortcuts, right? So so for example, oftentimes I will when I teach my classes, I will draw the structure of acetate like this. But I will ignore the counterion, right? The counterion is there. For example, sodium or potassium plus, right? But in organic chemistry, we often ignore it because it's just a spectator ion. So it doesn't participate in reactions, and it's not relevant. Most importantly, it's not really relevant for discussion. And so we often drop it. But we assume, we all know that the counterion is there. So kind of similar idea with the components of DNA. And the next slide actually will show you. So, let's continue the nomenclature. So these are deoxyribonucleotides. So you will need to know the structures, names, and symbols, 2-letter and 4-letter. So here the nucleotide. Let's start with the adenine. Okay, start with adenine. Adenine, so for the nucleotide, if it's a component of DNA, this will be deoxyadenylate. Alternatively, remember, you can call this as a nucleoside, but just add the phosphate. So there are two ways to name a nucleotide. You can name a nucleotide by itself, and then you will have to use the suffix ate. Or you can name the nucleoside and then add the phosphate to it. So in that case, it will be deoxyadenosine 5' monophosphate. And the reason why you may ask, why not just use adenylate all the time? There are, for example, with ATP, right? Remember ATP? Anybody remembers what ATP stands for?
Adenosine triphosphate.
Yes. So adenosine triphosphate. So in other words, it's very convenient to name a nucleoside and then state how many phosphates are attached. So for the nucleotide, you will have one phosphate. But there are other molecules besides nucleotides which are biologically very important. And so, for example, if you add one more phosphate, OP, and one more phosphate, so 3 total phosphates, this will be ATP. Actually, ATP, I think ATP has a hydroxy group, doesn't it? Yeah, I think ATP has a hydroxy group. So this will be then DATP, deoxyadenosine triphosphate. So it's very convenient just to name the nucleoside and then add how many phosphates you have. So, all right, so as far as the symbols, so you can see here, both A and DA can be used, even though A is misleading, because if you say just A, it looks like it's just adenosine, right? Or adenylate, but it's actually, it will be deoxyadenylate if you know that you're talking about DNA, right? If you know you talk about DNA, and remember, I told you, so A base pairs with T, G base pairs with C. I did not say DNA, D and DT, DA and DT, right? I just say A and T, even though these are this will be based on deoxyriboses. It's just because, again, we all understand that since it's a component of DNA, we can drop the D. Now, if I don't know, if I work with both DNA and RNA, in that case, I have to be specific and say that this is component of DNA and this is component of RNA. All right, and so the 4-letter will be deoxyadenosine monophosphate, which is this one. All right, does it make sense? So you see where A comes from, right?
Is there like
So-
a more, is
Go ahead.
there like a more conventional, like, because there's like so many different names, is there like one that people stick to, or are all of them used equally?
I've heard both. You know, I have read a lot of papers on as far as research papers go. People, again, depending on if you are dealing with the phosphates. So in other words, if you are subjecting your nucleic base to some kind of phosphorylation, dephosphorylation processes, right? So there are lots of reactions where you can remove one phosphate, remove two phosphates, add another phosphate, and so on and so forth, even ATP. So we talked about ATP, losing phosphate going to ADP, or gaining the phosphate going back to ADP, right? So if you are working with your nucleic base in the context of phosphates, then in most cases, the name of the nucleoside will be used and the number of phosphates will be indicated, okay? If it's just a nucleotide by itself, then the first version will be used, so deoxyadenylate. So it depends on the context.
Okay.
All right, so then guanylate. So now we're dealing with deoxyguanylate. Now also you can name the nucleoside, deoxyguanosine, and then 5' monophosphate. G, DG, DGMP. Deoxythymidylate, deoxythymidine, 5' monophosphate. T, DT, DTMP. And cytidylate, deoxycytidylate or deoxycytidine 5' monophosphate. CDC, DCMP. All right, will you remember that, you think? Not too many, just 4 of them. Just 4 of them. And for RNA, it will be same idea. There's a little typo here. You can see that this was copied and pasted. And so this D has to be removed. And this D has to be removed. And so this will be not 4-letter, right? It will be 3-letter. On this will be 1-letter then. All right, so here's the nucleotide, adenylate, right? So no deoxy anymore. So adenosine 5' monophosphate. And now you use A and AMP, adenosine monophosphate. Guanylate, guanosine 5' monophosphate. G, 1-letter, and 3-letter, GMP. Now instead of thymine, now we have uracil, right? So this will be uridylate or uridine monophosphate. And there's a cytidylate, C and CMP. And so here's the case where you will use, so instead of AMP, if you add couple phosphates, this will be ATP, adenosine triphosphate. So in this case, it will be more convenient to use the name of the nucleoside. All right, any questions? All right, so this is how nomenclature works. So let's talk about glycosidic, yes? No? Okay. So as far as glycosidic bond, so this will be an N-glycosidic bond as opposed to acetals like in carbohydrates, right? So we talked about the fact that this is going to be in beta configuration, right? So if you have a ribose, then the base, nitrogenous base, will be in the beta configuration. So this is the anomeric carbon. Anomeric carbon. And you can see here, so since this is up, this is up, right? They're both on the same side. It's a beta configuration. Beta configuration. Now, so as far as the nitrogenous base, so remember, as far as numbering goes, in pyrimidines, it will be nitrogen N1, and in purines, it will be nitrogen N9. So let's try to draw that. So let's try to draw a pyrimidine-based pyrimidine-based, let's say nucleoside, like that, right? And remember, so numbering goes 1, 2, 3, it's going to be 5, and that's going to be 6. So nitrogen 1. Now, I don't know if you can see that very well. Let me erase this and do a better job at writing 1. 1. Okay, in purines, it will be nitrogen 9, right? So here, remember the way we're going to do this. So first, we're going to draw the imidazole ring. Imidazole. So let me draw the, let's say, adenine. I'm going to draw adenine. Like that. And so the way numbering works, remember in purines, you start with that nitrogen. And actually, I gave you a link to a site where this numbering in purines is discussed. Remember, we talked about that at the previous lecture. And so it does look like for purines, the numbering does not follow the IUPAC rules. So, and I guess this numbering system was invented before the rules were in place, and so that the rules were never changed. 8 and then 9, right? So in purines, so this is adenine or adenosine. If you add ribose, so we have nitrogen 9, which is bonded to through the glycosidic bond to the anomeric carbon. Right, nitrogen 1 in pyrimidines, nitrogen 9 in purines. So the bond is stable towards hydrolysis, especially in pyrimidines. Can we answer that question? So why is this so? And if we read the next one, actually, the next bullet point, bond cleavage is catalyzed by acid. So why do you think glycosidic bond is more stable when the base is a pyrimidine rather than a purine?
Is it sterics or like size?
Well, hydrolysis, so the reaction will actually proceed by, it will be an SN1-like mechanism. And so what will happen is you have nitrogenous base, which let's say has another nitrogen, right? Let me draw it here. So this nitrogen will be protonated.
Does it have to do with aromaticity?
Aromaticity. Possible. I don't know. Well, let me draw the mechanism and maybe you can then. Maybe you can be more specific after I draw the mechanism. So there's another nitrogen, right? There's a lone pair reaching out to get the proton. You get the proton. It will be positively charged. Then the lone pair on the oxygen will kick it out. This will leave. This will leave to give you a carbocation, which is stabilized by resonance. I mean, that's why the anomeric carbon is reactive, is because there is resonance stabilization from the oxygen. And remember, in this resonance structure, all atoms have an octet of electrons, right? So here we have electron deficient species, carbon. Here, everybody has an octet of electrons. That's why it's a stable resonance structure. And then obviously water will come in. Water will come in, attack the anomeric carbon. And then you get, can be alpha or beta, right? And sometimes these kind of species are referred to as A basic species, which is which means that the base has departed, right? So actually, this is one type of DNA damage. So oftentimes, when DNA is damaged, there are different kinds of damage. And one of them is the formation of these A basic sites, where one of the nitrogenous bases will simply come off the DNA because the glycosidic bond will break down. Okay, going back to the original question. So this would be the mechanism. So this is the formation of this A basic ribose, right? And so it says here that the bond is stable, but especially in pyrimidines. So why is it more stable in pyrimidines? So aromaticity. So why would an aromatic system make it less?
Wouldn't a purine have more aromaticity than the?
Yeah, that's what I was thinking about. I was thinking about purines, not pyrimidines.
Yeah, purine's more aromatic. So why would more aromatic system give you a better leaving group?
It would stabilize the charges.
Right, but which charges are we talking about?
Every nitrogen or every member of that 5-member ring will become sp2 hybridized when it bonds to guanine. So which gives it aromatic.
Perfect. I don't know if it has to do with aromaticity because, well, because the lone pairs on these nitrogens, right? They're not perpendicular to the aromatic system. So in other words, so you're thinking of, for example, from OChem 2 or OChem 1, where you have, for example, benzylic carbocation, right? And you, and we know that this is stable because the aromatic system will stabilize the positive charge. Is that what you're referring to?
Yeah, that's what I was talking about.
Yeah. So the problem here is that the empty p orbital that has the positive charge is perpendicular to the pi system of the aromatic ring, right? So here the lone pairs, they're not perpendicular. Sorry, what did I say? Perpendicular? Parallel. Yeah. I should be parallel. So in other words, if this is your aromatic system, the p orbitals of the aromatic system are like that. And so the CH2 group, the carbocation, has a p orbital which is parallel to it. And then the electrons from the pi system can occupy this p orbital, right? So here it's not going to happen because these lone pairs, they're not parallel with the pi system. They're actually perpendicular. So the electrons from the pi system cannot, they cannot interact with these lone pairs or protonated species. But protonation in general, you're right. So protonation is just because there's so many nitrogens. I think that should be the simple answer.
And that nitrogen, those electrons don't contribute because it's already sp2 hybridized, right?
That's right. So these do not contribute to the aromatic system now.
So you're saying that pyrimidines would be more stable to hydrolysis because they have the less nitrogens?
Yes, less nitrogens, less lone pairs. So pyrimidines in general are less basic. So remember, it's the basicity of this nitrogenous base which will make this reaction go forward, right? Because the first step is the protonation. So pyrimidines actually, in fact, so this is going to be uracil base, right? So here, the lone pair on this nitrogen, is that accessible? No, it's actually delocalized on the carbonyl groups, right? It's like an amide. Amides are not basic at all. Amines are, like this amine is very basic, but this is an amide. So the lone pair is delocalized on the carbonyls. So pyrimidines actually not very, well, they may be slightly basic, but much less basic than purines, obviously. And so the purines, so when you, so this actually has much larger ramifications. So it's not just for us, it's a academic sort of discussion just for fun, right? It actually has significant ramifications in a way that DNA damage and the formation of the A basic sites in DNA. So purines are actually much more susceptible to the formation of the A basic site and to DNA damage. They're much more likely to come off and break this glycosidic bond. All right, that should be enough. Now, So there's N-glycosidic bond. So there's a rotation about this carbon-nitrogen bond, right, at the anomeric carbon. And so obviously this in purines especially, it's much more pronounced. So this can actually occupy two positions. It can be right above the ribose ring, or it can rotate by 180 degrees. So this will be syn. Syn means basically both the ring, the nitrogenous base and the ribose are on the same side. And so which atoms do we use for that? So let's say for purine, it's going to be O4 prime, which is this one. Oxygen at position 4 prime of the ribose, right? Then C1 prime, which is this one. Then N9, which is the nitrogen 9 of the purine, and C4 of the purine is this one. So now follow these four atoms, and you can see that this is a syn conformation, right? So if you rotate about this carbon-nitrogen bond, these two are on the same side. Now for pyrimidine, so this will be syn, but if this rotates by 180 degrees, right? So the this will be trans or anti, more correctly, anti. Like so. Now for pyrimidines, we actually follow this carbonyl here, and the most stable is the anti, in which the carbonyl is on the outside. And again, so we follow for pyrimidines, it's O4 prime, this atom, C1 prime, this atom, N1, and C2. This will be C2. Right, so this will be anti because they you can see that C2 and C4 prime are in the opposite directions relative to this axis. So it's anti-cytidine. Okay, and so when we talk about different conformations of DNA, so we'll find that bDNA is the most common one. And so anti-conformation is most stable, and it's found actually in the most stable conformation of DNA. You can see that there's actually quite a bit of steric hindrance. It's just like from OChem1, right? Anti is always more stable than syn because of steric hindrance. Why do you think in pyrimidines, why do you think this is more stable than syn? So if you rotate it by 180 degrees, so that the carbonyl is actually above the ring.
Is it because the two oxygens would be too close?
Yeah, I don't, for example, you're right. I don't like two oxygens being too close. There's lone pairs on oxygens, and lone pairs will repel each other, right? So electrons hate each other. So so normally these two oxygens would be kept apart in the most stable conformation. Now there's also what's known as tautomerism. So we talked. Let me see what else is coming. Okay. There's also tautomerism of nitrogenous bases. So remember tautomers. We talked about them in terms of ketones in OChem2, right? So remember in a regular ketone, so you have a hydrogen which can be attached to the carbon Alternatively, hydrogen can be attached to the oxygen. The hydrogen can be attached to the oxygen. Which one is, which tautomer is more stable? Anybody remembers?
The first one.
The first one. So the ketone is more stable than, so this is enol, right? Remember we refer to this as keto-enol tautomerization, right? Keto-enol. Enol means en, double bond, ol, hydroxy group, right? So enol. And so this is actually shifted to the left, and primarily due to the stability of the carbonyl group. So carbonyl groups, whenever we have a chance to create the carbonyl groups, do it. Carbonyls are good. All right. So so here we have some possibilities for tautomerism as well with nitrogenous bases. And so here is lactam, lactim. Tautomerism occurs in some heterocycles, and both tautomers exist in solution, but the lactam forms a predominant and neutral pH. So just like keto is predominant, lactam will be more predominant. And here are the two possibilities of lactim for uracil. So this is lactam, right? So actually both amide groups, right? They're actually in the carbonyl form. Now, if you have this hydrogen, so if this picks up the proton, right, and then the lone pair forms a double bond here. Here's will be a lactim, lactam, lactim. So, but the other carbonyl is still there. But if you do the same thing with the other carbonyl, now this comes and grabs this proton. This comes down this way, this goes this way. Then you get a double lactim, right? So now this was, the tautomerism is actually quite important. And originally when the structure of DNA was not known, this was one of the biggest impediments in trying to solve the structure of DNA by scientists named Watson and Crick, right? You know Watson and Crick, right? Who discovered the structure of DNA. So one of the major impediments they had to overcome was which tautomers these nitrogenous bases actually existed in, right? Which tautomers were most stable. But we'll talk about that on Monday.
Is there a way to control between like going just to one lactim or to the double lactim?
If there's a way to control it,
like how do you stop it at like just the lactim if you want it?
I would say you can obviously, since this is equilibrium, you can control this with temperature. At the moment, I don't know exactly how the temperature will affect the distribution between these. We need to know the equilibrium constants, right? And secondly, just from like my sort of intuition as an organic chemist, I would say that since here the protons are on the oxygens, so lactams are capable of better hydrogen bond interaction than lactams. Okay, so here the hydrogens are on the nitrogens, and nitrogen is not as electronegative as oxygen, right? And so even though the formation of this lactim, for example, double lactim, the beauty of double lactim, it's aromatic. It's aromatic, whereas lactam is not aromatic, right? Lactam has the advantage of having the carbonyl groups. So if you take this, let's say if this was done in a gas phase, then this would all be between who wins, the aromatic system wins, or is it the stability of the carbonyl group that wins? But since this, in most cases, this will be done in a solvent, right? So the solvent, for example, is capable of hydrogen bonding, such as water. So I would give preference to double lactim in this solvent, just because again, you have hydrogen bond, a better hydrogen bond donor, and now you also have hydrogen bond acceptor. Here you don't have hydrogen bond acceptor because oxygen is not such a great hydrogen bond acceptor because again, once you protonate oxygen, you get a positive charge on the oxygen, and it's electronegative. It doesn't want to be positively charged. Whereas if you protonate the nitrogen, it's fine for the nitrogen to be positively charged. So in other words, in the lactim, this is a better hydrogen bond donor, and this is a better hydrogen bond acceptor than these two in the lactam, right? So in water, I would favor this one. In other solvents, such as, for example, I don't know, chloroform, methylene dichloride, ether, I would favor this one because of the lack of hydrogen bonding in the solvent.
Thank you.
Yeah. Okay, so I think we're good for today. We out of time. Do you guys have any questions? So wait for the pages from me. I'll put them in the announcement. And I'll talk to you on Monday. Have a good weekend.
Dr. Kornico, I had a
Yeah.
really quick question about chapter 7. I was doing my notes for it. Do we have to know the actual linkage for amylose and amylopectin? Whether it's alpha, like I looked it up and I think it said alpha 1,3, beta 1,6, but I just didn't know if we need to actually know the type of linkage for that.
No, well, yes, you do need to know, but it's not 1,3. It's actually it's much simpler than that. So basically amylose and amylopectin, so all of these polysaccharides, starch, glycogen, right? They will have alpha 1,2 linkages. That's how they, sorry, alpha 1,4 linkages, right?
Okay.
But sometimes there's a branching.
Yeah, and it's 1,6.
That's 1,6. So that's all you need to know.
So it's all the same for all of them. Just it'll be different if it's alpha or beta. Because like I think glycogen and starch are alpha, and then cellulose and chitin were beta.
Yes. Mm-hmm.
And then we can't break those down because they're beta.
Yes. Mm-hmm.
Okay, perfect. All right, thank you.
Mm-hmm.